Good morning, everyone. Hope everyone had a lovely weekend. Getting back to another full week here, and no better way to start it off than with structural steel design. Last day we started talking about these forces that we can't really assess, and so there were a couple very important things there. There were dead and live loads, and the categorization of those loads were very important. Dead loads were everything that were permanently fixed to the structure. Live loads was everything that can move within a structure, including people, storage items, furniture, etc. And what else was important there was we represent these loads more or less as uniformly distributed over the floor area. We talked about how to trace uniform loads down through the floor system in lecture 3 earlier in the term, and so it's convenient for us to treat these as uniformly distributed loads. And as long as we're capturing that maximum moment in shear, that's all that is really important. The other thing that was somewhat important there was live loads are very unlikely to act in their full form everywhere in the structure simultaneously. And so I had introduced the idea of a live load reduction factor, which we rushed through a little bit in an example for a girder at the end of the day Friday, but we'll do an example of how a live load reduction factor might apply to a column today. And we have a bit more time to go through that example. We're going to continue on with new loads today, and trigger warning, it's tough material for us Atlantic Canadians. We're going to start talking about snow loads, okay? Now, I know it's difficult because we're slowly approaching the end of summer and fall's quite short for us, and the white stuff is going to be here sooner than later, but we need to talk about it now in the course. Basically, we're continuing on with section B, Division B, Part 4, section 4.1.6 today. And so again, I'm presenting the really important bits or the main highlights from the building code, but you really should go read the building code section 4.1.6. Not everything there is going to be important for you for this course, but everything in there is going to be important for you in your career if you decide to pursue structural engineering for the long term. So basically, continuing on in order here. So today we're talking about snow loads. That's in 4.1.6. And really what we're going to do today is focus on flat roofs that are relatively small. And I'll give you some context for why that matters. Basically, after today, you should be able to define, describe, and quantify the different factors that are used to calculate the design snow load. Okay, so basically, NBC gives us a big long equation with a bunch of stuff in it. We need to know what those factors are for and how to apply them. Once you can do that, you should be able to quantify the actual uniform design snow load for the roof of the building, and you'll have to do that briefly in the practice today, and we'll go through that example. And because this is a little bit short in terms of material, I'm going to go back, and what we're going to do, we've already looked at a joist, we've looked at a girder. Today we're going to look at the column in more detail. We're going to look at how to calculate the dead load, live load, and snow load on a typical heavily loaded column in our building. So we're basically going to put the stuff we'll talk about today together with the stuff we talked about on Friday to look at all the different loads that are acting on a column. Hey, does anyone have any questions about these things before we get into the material this morning? Great. So first off, just to get people engaged a little bit this morning, what kinds of things would you expect would influence the amount of snow on the roof of a building, for example, that we might have to consider as the engineer? What things would influence the design snow load that we'd consider when designing the frame members supporting the roof? Word cloud problem, basically type in the words. If you want your words to show up together, you can use an underscore, or I'm pretty sure you can put quotations around them. So weather is a pretty good word. Snow is basically a function of our weather. Roof slope, the weight or the density perhaps of the snow falling on the roof. Maybe I should extend the time limit on this a little bit more, about 15 seconds left. Temperature, environment, roof area, that's a pretty good one. Location seems pretty important. 5 more seconds to get a couple answers in there. All right. And yeah, maybe I'll extend that by 20 seconds or so for next year, but these are all pretty important things, right? So location. If you're down in Mexico, probably not a lot of snow on the roof to design for, but if you're up north in Canada, probably a lot of snow to design for, right? That ties in with the weather, past conditions. Oftentimes what we're going to see, and a consequence of what we usually do, we take past weather data and we basically do some statistics and say, okay, this is on average how much snow might be on the ground. And what we're going to look for is the return period for every 50 years. And we're going to say the maximum snow in 50 years is basically what we're going to design for. And that comes from past conditions. Now we're going to see, well, we're not going to see, but I'll tell you a little bit about it. That assumes stationary data, right? We assume that for thousands and thousands and thousands of years, the statistics will be more or less applicable to the locations that we're working with. But of course, everyone knows there's non-stationarity in climate. And so maybe there's going to be more snow in the future. Maybe there's going to be a little bit less. And that depends on what we expect to happen, but it's hard to predict. Snow weight, or that's probably good, snow weight. So the density of the snow is going to be important. The area of the roof is actually going to be important. We'll see that depending on how big the roof is, you may have more or less snow. Sometimes the wind likes to blow snow around as well. If you have a small roof, the wind's basically going to blow some of that off. But if you have a really big roof, the wind's just going to push it along. Temperatures, of course, kind of tie in with location. Slope of the roof is another important one there. I'm assuming that's what you mean by whoever put that in was roof slope. Really steep roofs will see snow tends to slide off or get blown off by the wind, and flat roofs, the snow tends to accumulate. Okay, so those are all great words, and we're going to talk about what some of those mean for us here, getting into snow loads again, which is 4.1.6 in the building code. What 4.1.6 tells us about calculating the snow load is we need to consider a whole bunch of things. Okay, so the snow load that we're going to calculate and apply to the roof area is this value S. Okay, that's the 1 in 50 year design snow load. And it's a function of a bunch of stuff. Okay, so we've got something called an importance factor. We've got a 1 in year ground snow, a 1 in 50 year rain load, something, and then a bunch of C factors, a basic snow load factor, a wind exposure factor, a slope factor, and then accumulation factor. Roof size is going to come into play with the accumulation and the basic snow load factor. Weather and exposure is going to come into play mostly with wind exposure and some slope to count for the slope of the roof. And then the location. Basically, we're going to figure out, okay, if we're in Fredericton, we're going to see what the ground and rain loads are for that area, and we're going to plug them into this expression. And of course, an importance factor we're going to see basically augments the risk that we're willing to accept associated with the snow load we're designing for certain types of structures. Okay, so importance-wise, you might think, well, some buildings might be more important than others, right? So hospital, pretty important. Nuclear generating station, probably pretty important. You don't want anything to go wrong with these types of structures. Basically, if you're living in a regular residential space and you get a ridiculous amount of snow you didn't account for, your roof might fall down, you might get injured, you need to go to the hospital. The roof better not have fallen down in the hospital, right? That's pretty straightforward. High importance might be something like a school, right? Usually schools might even fit into post-disaster. It basically depends. If there's a school that's designated as like a, you all have to go to this school after this disaster happens kind of school, then you're going to design that as post-disaster, but most of them tend to be high. And if you're just throwing something up to, I don't know, be a temporary structure, sometimes you might have, I don't even know what I would quantify as a temporary structure, but you might just put up a structure on your campus because you're too cheap to build something proper. It's only expected to be there 20 years, so you might consider that a low important structure in terms of how long that building is actually going to be there in place. In this course, we're basically going to be looking at a normal importance for most of the cases that we're looking at. And I'll come back and talk later on about what these ULS and SLS values mean. This is basically designed for strength or safety. This is designed for serviceability, or you could also call it usability or comfort. And we'll talk about when to apply these different kinds of factors for these different kinds of calculations. Then we've got the climate data, and this ties into the location and past conditions. Okay, so this is just an excerpt from table C2. Section C of the building code is an appendix that includes all climatic data. It includes snow load data, wind data. For the mechanical engineers, they're going to look at something like degree days below 18 to figure out what your heating load might be. And there is some other information here in terms of design temperature for insulation and stuff. All this climatic data falls into the design of different components of buildings, but us as structural engineers, we're going to focus on snow and lecture, we'll talk a little bit about wind. Basically, if we were designing a structure for Fredericton, and we'll see this later, we're going to look at calculating the snow loads for Fredericton, then what we would do is say, okay, we're going to go to Fredericton, and we're going to look at these values here, the 1 in 50 year snow load and rain load values. Okay, so SS for Fredericton is 3.1, SR for Fredericton is 0.6, and this comes from people actually doing statistics on measured snow values to figure out what these might be with a return period of 1 in 50. Now there's this basic snow load factor, and it used to be super simple, and it was just always 0.8. Always 0.8 up until about 2005 in the building code. What the basic snow load factor is trying to do here is tell us that most of the time, and really where this came from, they basically said, okay, back in the 50s, we went up on the roof and we measured the depth of snow on the roof, and if we did that everywhere, on average, the snow on the roof was 80% of the snow on the ground. And that's really as simple as it is. If you have a small roof and snow falls on it, basically there's a part of aerodynamics, the snow is going to fall and kind of go around the building, so it's not all going to fall on the roof, it's going to fall on the ground. And from time to time, the wind will come and blow some of that fresh snow off the roof, and it will settle on the ground around the structure. Okay, so it's as simple as that. Now, they got in trouble because at some point they realized that for really big roofs, right, if L and W are really big, basically if you have a huge roof, think about these new single-story Amazon warehouses, for example, or Costco buildings, huge structures. The wind doesn't just come and blow the snow off the roof. It comes and it blows the snow at the front of the building downwind to the other side of the building. And so, in fact, it just accumulates and piles up further on down the structure. And so we need to design our elements to account for the fact that we might get snow pile up. If the wind comes this way, we might end up getting a bunch of pile up snow at the far end rather than having it get blown off the structure. Okay, so how this is determined is through this characteristic length. They call it LC. And what LC is 70 divided by CW. Or sorry, no, that's it's 2 times the short width of the structure minus the short width squared divided by the long length of the structure. And if it's less than 70 divided by our wind exposure factor squared, then we get to use our 0.8. Okay, so this would be the defining line between what would be called a small roof. Okay, so for small roofs, CB is 0.8, as defined by this characteristic length LC. And for large roofs, our CB factor starts to get a little bit bigger. Okay, so what that looks like here, small roofs tend to be in this range, and we're going to talk about wind exposure in a second. But for a wind exposure of 1, which would be typical for most structures, this is basically LC is equal to 70, right? So LC is 70 divided by 1 squared. This is the small roof range. This is the large roof range. And we'll see for typical areas, basically we saturate ourselves at ground snow load. Okay, so for big roofs in typical areas, the wind just blows the snow and we might get something equal to about the ground snow load, which seems to make sense. For areas that are really exposed to wind, we're going to get wind blowing more snow off for larger roof areas. But as the roof gets really big, that wind's just going to add to the pileup downwind. Okay, so basically we have 3 different functions depending on how windy and how exposed our structure is going to be to wind. But for the most part, most structures tend to be playing in this range. Most structures, especially office structures, residential structures. The only buildings that tend to be more in the large roof range are those single-story, really big mega warehouse structures, and that's when you have to start considering an increase in your basic snow load factor. That takes us right into the wind exposure factor, and for this course, we're going to take it as 1. And the reason for that is, for the most part, we're working in urban areas. And what sentence 4.1.6.2, sentence 4 of the building code says is this is usually taken as 1, but you could reduce it to 0.7 in rural areas. In rural areas, you have fewer buildings around it. You have a building in the middle of nowhere. It's surrounded by nothing but trees. You can use 0.7. More wind is likely to blow some of that snow off the roof. Or north of the tree line, you can actually reduce it to 0.5. Does anyone know what north of the tree line means? I didn't know this until like 3 years ago. What, has anyone heard of the term north of the tree line? Anyone work up north before, like Northwest Territories, Yukon? None of it. The tree line is basically an area, literally, trees stop growing. Okay, so below this line, the trees grow here, and it's pretty sudden. I've spoken to some people who worked up north, and they look, you literally see the tree line. Trees just stop growing at a certain point when you get far enough north. That means you have a building in the middle of nowhere with no trees, and there's plenty of wind there to blow snow off, and so you get a wind exposure factor of 0.5, helps you for design snow load, doesn't help you for really big roofs. Now, the problem here is, again, with the non-stationarity and what's going on with temperatures and average daily or average annual temperatures, they're sort of noticing that the tree line's starting to creep a little bit further north as that area starts to get a little bit warmer. And so it's probably not a very good idea to design for 0.5 even in that area, because it might be covered in trees at some point, and all of a sudden your snow load goes up by 0.7 over 0.5, maybe, what's that, 40%? That's a pretty big increase in snow load. And of course, if you've got structures around for a long time, maybe you've got a small town that's currently considered urban, all of a sudden you've got all these great big structures built around it, and there's no more exposure to wind. It's almost always a good practice to just take CW as equal to 1.0. We've got a slope factor CS here, and basically what that's accounting for is on a flat roof, the snow falls and it stays there. But for really, really steep roofs, snow starts to fall off, or it doesn't even accumulate on the roof at all. And there are different kinds of roofs. There are slippery roofs that don't have anything holding on it. Anyone have like a steel roof at their house at home? Does snow accumulate on your steel roof at home? It just slides off. Right? You can put a little snow fence at the bottom to kind of keep the snow up, and in that case, it's unobstructed. Or if you have a snow fence, it is obstructed, and you have to do for most roofs. But if you have a steel roof with no snow fence, it's basically going to slide off. And if you think about these angles, right, 70 degrees. 70 degrees is, that's like that, right, like super high pitch. Anyone think of any structures that might have like a 70 degree or greater angle? What's that? Yeah, a roof of 70 degree pitch. What kind of structure has that? Yeah, it's a steeple of a church, right? The cathedral downtown, it's like this steep, roughly. Ever see snow on that roof? There's no snow on that roof. It just falls off, blows off, slides off. There's no snow on that roof. So we can actually use a factor of 0 when we're designing structures like that, which basically means most of our snow load goes to 0 when we're designing those kinds of structures. Okay, but it's important to differentiate between what is a roof that's most likely going to keep the snow on the roof versus what a slippery, unobstructed roof might be when you're making these kinds of determinations. Okay, so we've talked about a few things here. We've talked about importance factor, we've talked about the climate data, and we've talked about these 3 factors here. Basically, we have a factor to account for the fact that snow on the ground is different from snow on the roof, and so we've got a factor to account for that. We've got a factor to account for the fact that wind sometimes blows snow off the roof, and we've got a factor to account for the fact that snow tends to stay on flat roofs and fall off of angled or slippery roofs. Does anyone have any questions about any of those factors that we've talked about so far before we keep going here? I think they're pretty straightforward. The last one we're going to talk about is CA here. And in this class, we're going to be dealing with flat roofs that don't have any obstructions on them. So for the purposes of what you do in this course, just take it as 1. What this factor is to account for, though, is the potential that we can get snow drifting, especially when we have multi-level roofs, or more common, a mechanical penthouse of sorts on the roof. Right? If you've got an elevator motor, or you've got HVAC equipment, or any other services that are primarily supported by some kind of mechanical infrastructure, there's usually a penthouse on the roof that has all that stuff. Not the fancy penthouse, like the $1 million penthouse that all the lawyers buy, but the stuff where it's quite dirty and all the mechanical equipment goes. As the wind blows across this roof, the snow's going to blow, but then it's going to basically hit the wall and not go anywhere, right? And so basically they're going to be pushing snow up against that wall, or there's a potential for wind to blow this way, and all of the snow that's on the roof here comes down and accumulates, maybe something like that, on top of the snow that might have already been there. And so this is basically a factor that accounts for the potential for snow to drift up against roofs that have a different height elevation than the flat roof that forms the structure for the most part. But in our case here, and in this course, just take this factor of 1. And we're not going to talk about calculating the accumulation factor, but I do want you to know that it's there and that it's an important factor to consider. It's very unlikely that you're ever going to design a roof of a structure that doesn't actually include the accumulation factor. Hey, any questions about that before we move on to a small exercise? Not like exercise like this, but mind exercise. Okay, so I'm going to get you all to do some work now then. What I want you to do, all the information is actually available in the slides to do this problem. I want you to calculate the specified snow load for a building of normal importance with a small flat roof in Fredericton, New Brunswick. Okay, and there are 6 available answers here, and they're more or less there to mess with how you apply the factors. But there's an equation in the slides on how to calculate the snow load. There are tables in the slides that give you information about importance, etc. And there should be enough information in there for you to put all of that together and calculate what S would be for a flat roof in Fredericton. Okay, so I'll give you a little bit more time here, maybe a couple of minutes. This is something, if you want to talk about it, you're not sure, please talk with the person next to you or the entire table that you're at, people in front or behind you. Just think about it for a couple minutes. Once you're happy with an answer, you can put it in. We'll come back and talk about where this comes from after. It's a great time too. If you have any questions, you can put your hand up and I can come answer that. That way you don't have to ask your question in front of everybody if you don't feel comfortable doing that. All right. I get the impression that any discussions that are going on now are occurring between those who have either already determined what their answer should be or who aren't going to try it, and that's fine with me. But we've got 16 or so folks piling up on, thankfully, the right answer. Okay, so the right answer here is 3.08 kPa. Was the math very hard to do that? 95, 99 even percent of the time, structural steel design, the math is not going to be the problem. All right, what's going to be the problem is deciding what to do and why you're going to do the math that you're doing. Okay, so here was calculate specified snow load for building in normal importance with small flat roof in Fredericton. Okay, there's an equation that we've been working with, and that's this one. S is the factor times, in brackets, ground snow times a bunch of factors plus rain load. And what we need to do is figure out what these factors are going to be and why we're going to use those factors. Okay, so what importance factor did people use to calculate the snow load? 1, normal importance structure. You go to importance category table, and we see normal importance gets a importance factor of 1. Then we have the climate data. What did we use for SS and SR? In fact, I already told you what they should be. We used, that's right, from the table we used 3.1 for SS and 0.6 for SR. Why? Because we're in Fredericton, right? We're not somewhere else in the province. We're in Fredericton. We can rely on the fact that this information is reasonable. If these are interesting, right? If you're in Bathurst or Campbellton, you've got significantly larger numbers. Versus if you were in, I guess St. John didn't quite make it to the table here, but St. John, those who live there know that there's not a whole lot of snow in St. John. Snow loads are significantly smaller. Then we had basic snow load factor. What did we use here for CB? 0.8, right? Why? Well, I said in the problem it was a small roof. I didn't give you any information about the plan dimensions. I said it was small. And for the most part, if you're in like a typical apartment building or a house or something, it's small and you'll know automatically you don't need to calculate this LC value. It will just be a small roof and you know that CB is equal to 0.8. And then we said, okay, we've got CW, and in this course, we always take CW as 1 because it's the conservative thing to do. And if you're reducing it, there are things that can change over time that might not allow it to be those reduced values anymore. Okay, so it's important for us to recognize when it's more or less appropriate to do that. And in our case, we're going to take a value of 1. Slope factor, well, I said it's a flat roof, right? Which means the slope is 0. Slope of the roof is alpha here. If it's less than 30 degrees, we don't get any reduction. Doesn't matter if it's slippery and unobstructed or if it's a most roof, a typical roof. In both cases, flat roofs, CS is going to be equal to 1. And of course, finally, we had an accumulation factor. We'll say, I said, take it as 1. If there is a penthouse on the roof, that might change in certain areas, but where the snow is still uniform on the roof, it's not going to pile up over the entire roof. Where the snow is uniform, we're basically going to take that as 1. Okay, so we get all those values, we mash them together. Pretty simple math. We just have to know when and where we're using these values. We get 3.08. I'm going to round that to 3.1. The 3.1 on the Poll Everywhere slide was basically a, in case you just wanted to take SS of 3.1, you might have gotten it slightly incorrect there. I want to make sure that I corrected that misconception. But in my case here, I'm going to, and it's quite typical for me to round these up to just 2 significant figures or a single decimal place when talking about these snow loads. Okay, does anyone have any questions about that problem or concerns about that problem? It's pretty simple. You're going to have to do it for your design project. Might have to do it on an exam. Certainly going to have to do it for a quiz. All right. This is basically the entire snow loads lecture. Figure out what these factors are, describe what they're for, put them together to get a uniform snow load. Okay. Learning objectives 1 and 2 done. All right. So that's all fun. And that's basically the end of the stuff on snow loads. So we've got 20 minutes or so to go through a slightly more detailed example. And what we're going to do is we're going to put together some of the stuff that we talked about the other day with some of the stuff we talked about in lecture 3. In lecture on Friday, pardon me, we had gone through where I showed you briefly an example of a floor inside the structure where we might have a dead load of 4.8 kPa, right? I showed you that cross section of the floor, and there's mechanical stuff and lighting and framing and whatever, and that added up to about 4.8 kPa. I didn't do that for the roof, but I'm just going to take a value of 2.8 kPa for the roof of the structure. Okay, so from the dead loads lecture, Friday we had 4.8. I'm assuming 2.8 for the dead load on the roof. The problem here is the same story structure that we've been looking at throughout the course so far. It's going to be primarily used as office space, which should tell us some things about live load and whether or not we're allowed to reduce the live load. And we're also going to look at the snow load, which we just calculated. Okay, so the problem here is we've got a 4-story structure. It's got this dead load on the interior floors, a different one on the roof. And we have the snow that we just calculated, and we can figure out some live loads for us here. Okay, so our goal is to figure out what the maximum compression from each of these forces might be on a typical column at the bottom of our structure. Does anyone have any questions about what this problem is asking us to do before we get into the details? Okay, so basically what we have here is we need to determine, first of all, what the live loads are going to be. We've got an office space, okay, so we need to go to not this table all the time, but we do need to go to the table in the building code and figure out what the live loads are going to be. We've got an office building, right? So we've got office areas, and we're going to look at the floor ground level, and we'll talk about why that is in a minute. But for office areas above the ground, we're going to use 2.4 kPa, okay? Go to the actual building code table to find that value, but I've just got some of the important in this slide. The other thing that's important for us is we have to look at the roof, okay, minimum live load, and for roofs where the snow load doesn't exceed this value, we're going to use a value of 1 kPa. Okay, now what's important here is that we're only going to ignore this when the snow exceeds 1 kPa when we want to consider snow when we're adding these forces together. Okay, so we'll talk a little bit more about what that means in lecture 10. But for now, we're going to look at a live load on the roof of 1 kPa. We're going to look at a live load for the office area is 2.4 kPa. And we're going to keep these separate. We cannot reduce roof live loads. We can reduce office live loads. And so we'll come back to that when we do those kinds of calculations. So what we have here, whoops, I went way too far ahead. This is the problem. We've got column B4. Maybe I'll go back briefly. And so column B4 is this one, right? Column line B, column line 4. It's got 4 levels to support. So we've got snow up to 3.1 kPa. We've got a roof live load of 1 kPa and an interior live load of 2.4 kPa. So the darker ones are the office, the lighter one is the roof. And then we've got dead loads, roof and interior floors shown here. And what we need to do is figure out what is the total compression on the bottom column going to be under these applied loads. So we're going to start with snow. We just calculated this value. Again, this is 3.08, rounded up to 3.1. It's not the ground snow load. And in lecture 3, we calculated a tributary area for this floor level of 78.75 meters squared. Okay, so what we're going to do is we're going to start with the snow load. How do we figure out what the reaction at the base of this column should be? How do we put these values together to get the snow load compression force on our column at the base? Is there any snow inside the building? Is maybe the first question. No. That's the first mistake that happens, is snow load gets applied to all the floors. That's wrong. When the building's all closed up, we've got the snow load only acting on the roof. Is there any other force other than the snow there for that one section that we have acting on the column other than the snow on the roof? No. Right, so we've got the snow on the roof. Okay, so we're going to calculate that compression on the column due to the snow. That's just going to be equal to the snow load multiplied by the tributary area for the roof level. So I might say tributary area for 4. The area for these floors was all the same. They're all 78.75 meters squared. We've got 3.1 kPa acting over that area. Force is pressure times area. So that's going to be 3.1 kPa multiplied by 78.75 meters squared. And that's going to give us a total snow load of 244 kilonewtons. Okay, so what that means here is the total force supported by the column at the base from the snow load only is 244 kilonewtons. Have any questions about that? That's the simplest calculation we're going to do. Okay. Next, we're going to look at the live loads. And again, like I said previously, we're going to separate the live loads out by occupancy. We've got office space live load, minimum roof live load. We're going to look at those as 2 separate actions because they get treated differently when we start to add stuff together. And some of them can be reduced while others cannot. Okay, so what we're going to do here first is we're going to calculate CL and CLR. Maybe I'll start with the live load on the roof, CLR. The live load on the roof is 1 kPa. There's just the single floor that has the roof live load. So we're going to calculate that as the roof live load times the tributary area for floor 4. That's 1 kPa times 78.75 meters squared, which is 78.75 kilonewtons. I might just say, I'll call that 79 kilonewtons. Okay, so very similar to the calculation we just did for the roof snow load. Different load, same area, slightly smaller load. Questions or concerns about that step? Okay. Now we're going to look at the office live load. Whoops, I keep going to the wrong slide. Office live load. And that is going to be present over 3 floor areas. Okay, so floors 1, 2, and 3 all have this uniform office live load. And so there's going to be a tributary area of office space that this column is responsible for supporting. Okay, so what we're going to do first is we're going to calculate the tributary area for the, I guess we'll just say the regular office live load. That's going to be 3 floors worth of 78.75 meters squared. So the total tributary area worth of office space that column is responsible for supporting is 236.25 meters squared. The total live load, I don't know why I made that little squiggle. That's kind of ugly. The total live load then is going to be equal to the live load times the tributary area of the live load on the column, which is the 2.4 kPa multiplied by the 236.25 meters squared. That's going to give us a total load from the office space of 567 kilonewtons. Are there any questions about that? We've got 3 floors, all of the same area. We're going to split this up in terms of tributary area of office space. This column is responsible for supporting 236.25 meters squared worth of office space. The corresponding design dead load from that uniform load over that full tributary area is going to be 567 267 kilonewtons. Any questions about that? Are we done with that? Are we done? Live loads? What should we be considering here? So dead loads would imply we're done with the live loads, right? Yes, we do also have to look at live loads, but from a live load perspective, have we completed have we considered everything we should be considering with respect to live loads acting on this member? Some shaking heads. What is left for us to consider? Yeah, the potential to have a reduction in this live load. We're not, depending on how big the tributary area is, it's less likely that we're going to have the full 2.4 kPa acting over the entire 236.25 meters squared worth of floor area. Okay, so we need to determine whether or not we can and should be reducing the live load acting on that column from the office space occupancy. And for that, we can come to our flow chart that we looked at in lecture 5 on Friday. The first consideration is this an assembly area or similar? And we did this in lecture on Friday when we were looking at the tributary area for the girder. No, great. That's exactly the answer. This is not an assembly area or similar. So we've got an office live load. So we come over and we skip all the other stuff and come down here. Is the tributary area of the occupancy space we're considering bigger than 20 meters squared? It's a lot bigger. It's 236. It's an order of magnitude more than the 20 over which we need to consider the full live load reduction. So yes, we have a live load reduction factor that we can consider, and we calculate that as 0.3 plus the square root of 9.8 over the tributary area worth of that occupancy space. Okay, so our tributary area is 236.25. So our live load reduction factor is 0.3 plus the square root of 9.8 over 236.25. And if we do that calculation, we end up with a live load reduction factor of 0.504. Okay, so that's pretty sizable. That means we're only designing for half that force, right? If you were trying to keep costs down, would you not want to consider a reduction of 50%? I sure would. Okay, so what that means is we can take our 567 kilonewtons that we calculated, we can reduce that by multiplying it by 0.504, and I'm going to denote this as CL star. Star is going to, when we talk about live loads, is going to denote that that's the reduced value. I don't use R because it's confusing with roof, and so I'm just going to denote it as star. So live load star, or the reduced live load, is 0. Or maybe I'll just write this out as live load reduction factor times CL, which is 0.504 times 567 kilonewtons, right? Right. And that means my reduced live load is going to be about 286 kilonewtons. Okay, so a lot of live load really, as despite the fact that I'm carrying 3 floors worth of live load. At the end of the day, once I reduce it using my live load reduction factor, it's not significantly different from the snow load that the column is responsible for carrying, right? So the actions on this particular column end up being pretty similar when we compare the roof to the roof snow load to the total live load on that column. Okay, any questions about that live load reduction factor, how we determined it, how we calculated it, or why we were able to apply that value to the live load on the column in the first place? Okay, now we're done with the live loads for that particular member. Okay, so we've got for the roof live load 79 kilonewtons, for the 79 kilonewtons for the roof live load, 286 kilonewtons for the reduced live load on the bottom column. Now all we have left here is the dead loads. This one's pretty straightforward compared to even the live loads, and we don't have to separate these out because the dead load is what the dead load is. Okay, we don't have to separate them for reduction purposes. So all we need to do here is figure out, or consider really, I guess, which floors are carrying which dead loads. So I might write this out as the dead load on the column at the base is going to be equal to the 2.8 kPa worth of dead load over the roof, okay, which has 78.75 millimeters squared of tributary area, plus the 4.8 kPa over 3 floor areas of 78.75 meters squared. That's a relatively straightforward calculation. Do I not have it here? I do have it. If I consider those acting together, I get 1,355 kilonewtons. Any questions or concerns about that calculation? Okay, so if I was to come back then, I've got 1355 kilonewtons acting at the base of that column, and I kept going to this slide mistakenly, but this is basically the result of, I guess you would consider this a structural analysis. We have the loads on the floor areas, we've got the tributary areas for the different floors. We only have snow on the roof, that amounted to 240 tons. We have live load on 3 floors from office space that could be reduced based on those areas to get 286. A live load on the roof to consider of 79, and then a dead load of 1,355 kilonewtons. What's interesting to me, what stands out to me anyway, is the biggest one. Which one's the biggest? Dead load, by a reasonable amount, right? So the dead load is always going to be a significant load acting on these kinds of columns. For the most part, the structure is 70% responsible just to stand there by itself, and maybe 30% responsible for carrying some other loads like dead and live loads, okay? So that's for the bottom column. We're going to stop there for the example. But how would that be different if I was looking at this column? The one between, this is story 1, column 2, and 3. If I was looking at the third story column, what's different there? Yeah, so if I'm looking at this column, that column's not supporting those 2 floors, right? That column's not supporting these 2 floors. It's just supporting the weight above it. Does it change the snow load on the column? No, this column is actually responsible for carrying the same snow load at every level. Because there's one, it's a point load at the top. That one has the same load, which is that one, which is that one, which is that one. Dead, just carrying the roof and the upper floor. This is a little bit more complicated. It's carrying the roof and 1 floor above, but what else is different about my calculations if I was looking at that specific column? The live load reduction factor would not be the same, right? The tributary area is different. That column is just carrying 78.75 meters squared of office occupancy. I can still reduce it because it's more than 20, but it's not going to be as big because it's not 236. Okay, so those are some things to consider. That column is going to have a different live load reduction factor depending on what level you're looking at, as well as the fact that the loads are going to differ from column to column. Okay, well, now you should be able to do the things I said you should be able to do. That's describe and define and quantify those factors used to calculate the design snow load. You had to do that in lecture today to be able to calculate the uniform design snow load for the roof of a building. And finally, we went through an example of how we might look at those loads separately and determine what the actions from dead, live, and snow load might be on a column in a typical building. We haven't added anything together yet. We're just looking at actions for these different types of gravity loads. We'll talk about how we combine these effects in lecture 10. Does anyone have any questions about any of these objectives or any of the stuff that we talked about today before closing lecture for the morning? Okay, we'll be in lab this afternoon. This is not a computer lab. This is going to be a hands-on play with toys lab, right? And what I mean by that is I'm going to try and give you a sense through, they call it tactile learning or some other fancy word because people who do educational theory like to use fancy words for touching stuff. And basically what we're going to look at is some simple models of structures that you can build. You can see how difficult it is to build structures. You can see what happens when you push on it to the bracing system. We're going to look at what happens when you have the floors in certain places or if you don't have the floors. And we're going to focus on lateral loads on structures. They're not the best models for gravity loads, so they work sometimes. We're going to be spending time in person in lab this afternoon So please don't not show up. I'm not going to record it by Teams because I'm not going to videotape everyone playing with toys and lab, okay? So if you want to be there and get something out of it, then show up. Otherwise, we'll see you in lecture on Wednesday morning.